This is all I got so far. Okay. And I'm going to go right to here to stop. Okay. So remember that for free energy, the three conditions, you can have delta G positive, negative, or zero. And then if it's delta G is zero, then the system's in equilibrium. Okay. If that's the case, then when you go to this final equation down here, didn't. We'll leave you at that for just a minute. Get rid of that.
Okay, that makes more sense.
Yeah. Just so we know that.
So the whole last term drops out, right?
Yeah. Wait for it. Thinking about what I want to go through. So, yes. Okay. So, and I've got cover that. Okay. So then if the Q is zero, I want to make sure I say this the right way. If Q is equal to zero, natural log of Q, this term drops out, delta G is equal to zero. Well,
So if Q is equal to
yeah, so at equilibrium, you got concentrations equal to 1 molar, then the natural log of 1 is 0.
yes.
Okay? And then delta G is also equal to 0. Then, you're trying to figure out boiling point is what? You got this other equation. Okay? And if the delta goes on there, if delta G is equal to 0, then you have this thing 0 equals okay. And then finally, you can rearrange this thing to be stop right there and say this, that at the equilibrium where delta G's are 0, then you can write this, you can rearrange it to say the temperature for this particular condition at delta G equals 0, you can solve for it. And that'll be your boiling point. Okay. So then, with the appropriate data, could you figure out delta H and could you figure out delta S? You had the right numbers. In other words, these are not things I'd ever ask you to memorize. But if you had index.
When do we know when to put the distilled degree symbol and when not to?
If you had all that stuff, could you figure out delta H and delta S?
Yeah.
Okay, so I can skip the how to solve that.
I don't know.
Fine.
I don't suggest you do that.
Yeah.
No?
I don't suggest you do it.
Okay. Oh, let's see.
It's just like the same equation but with different numbers, right?
Yeah, I think I wrote them all down. this one is, I go delta H across the top, and I go delta S across the bottom. This is negative 106.7, and the liquid is 139.3. Make sure I have this right. And then the delta S numbers are okay, so if you had those numbers given to you, could you figure out delta H and delta S? Oh, okay. And just over here on the side, remember that it's the sum of the number of moles delta H products minus the sum of the number of moles delta H reactants. And in this case, if you do the math, you get positive 32.6. Okay. Same thing for the delta S numbers. You'd say you have the sum of delta S products minus the sum, I'll make that now, delta S reactants. The number you get here is, I'm going to convert it to kilojoules. Okay, stop right there. What questions do you have at this point? Mike?
Back up to the formula, you have negative RT natural L cubed. Isn't it negative when you have K? Or negative? Blue line.
Yeah. We go back up to rearrange. Set that equal to 0, rearrange to the side,
Okay, I see.
and then you get the negative. And then you're right, you'll use that when it gets into K, that shows up on down here, a couple of examples, but yeah, I got that there. Back.
So that equation that you wrote with the temperature is equal to delta H over delta S.
Mhm.
So that would apply to any system at equilibrium?
When you're trying to find, like this, yeah, and you're trying to find the boiling point.
Because it's but you could use it to theoretically find any temperature given the delta H and delta S values at those temperatures, right? Like freezing, I guess.
I haven't tried that, but theoretically, yes.
Okay.
When you're looking at a state change.
Right.
Because you got the state change, you got the equilibrium between
Right.
solid and liquid or liquid and gas.
Gotcha. Okay.
So then it's a matter of just plugging in the numbers, and in this case, you have positive 32.6, and on the bottom you have positive 0.095, and you get kilojoules per Kelvin. These disappear, and then your answer becomes
343.2.
questions about that one? And in particular, I want to make sure, like, and highlight it. That part's good. If you have the numbers, okay. Because I got one more example up here. This is the model. I want you to try one. I'm just going to give you the delta H and delta S with the assumption that if I gave you the like the data from my appendix, you could actually calculate it. Just to kind of speed things along. Okay. So fresh paper. And we'll go That's the question. If you've got that one handy, that's the model on how to solve this. And I've already done the delta H and delta S work. So let's freeze that. You get an answer yet?
Yes.
And it is.
330.2.
27.1 electricals.
I did switch it.
What?
33.
There you
Okay.
go. Okay.
She's writing.
Any questions? Seems reasonable? Okay. Next. Yeah, Chris. If it's at equilibrium, well, because why not, right? So when you're looking, and the thing about the equilibrium part, when you go to that standard temperature pressure setup, and I figured out why I went 25 last week. It has to do with electric chemistry, by the way. Because standard conditions in electric chem are 25 C. Why I couldn't find that answer. Anyway, but in order to answer yours, when you've got the Q is going to equal 1 over 1. So then the natural log goes to 0, and then there you go. But when you have this where you, number one, you have non-standard temperature, and you've got non-standard pressures, and they're not 1 atmosphere. Now you've got to deal with delta G being something else. Okay. Sit up. So, Curtis's question, you'll notice here this is I can write non-standard, cross that out. Non-standard conditions. Temperatures not 273 and not 1 atmosphere. So then the question is, what do you do? When you've got this, okay. With just the information that's on there, what can you solve?
Q.
Q. Okay. Remember, Q is going to be done with pressures and temperature, concentrations, and you've got pressures here. You can calculate Q, and remember, you got to remember to pay attention to coefficients on this one. And you should get that number. The box around that one. And then you've got T equal to 298K. And then remember, R for this one is not the ideal gas constant, but it is
Shouldn't the 3 be cubed in that one?
yeah.
Okay.
Okay, I still don't understand the little degree symbol and not having a degree symbol.
So this is going to be non-standard conditions,
Okay,
like
and standard conditions is, will be
0
told
Celsius.
when it's not standard, right? Or do
yeah,
we just have to guess?
If it's not at 0
20.
C or 273 kelvins, that's going to be a non-standard temperature.
I thought we've been operating at 25 degrees.
25 goes with electrochem. 0 goes with everything else.
So everything else is 0, that's standard.
Yeah.
So,
And I wasn't looking for the answer. I don't know. I couldn't find the distinction, and I don't remember, to be honest. So it is what it is. But there you go. Anyway, this is going to be your standard conditions,
okay.
and that would be based. You know, like you're trying to solve delta G. That's where you've got this data. So you'll have an appendix, or I would give you the information you would need to calculate this one. Okay. So this right here, let me go
And Q is just like
non-standard,
it's just 3 equivalent, okay.
okay, conditions, and that's what you're trying to find. This one over here, non-standard. Okay. In this case, let me put this in here. Do you remember your delta? I'm gonna put it up on top. You remember delta G for elements?
No.
That was 0.
So let's go to nitrogen. As gas, delta H is the first column, delta G is the second column, delta S is the third column, or S is the third column. Okay. So for your elements,
0.
zeros. Hydrogen, here's your hydrogen over here, zeros. Okay. You end up with then delta G at 0, 0. This one is negative 16.66. Okay. So, can you math that one in your head? What's delta G for the equation?
0. In the bottom. 13.66. Well,
Oh, it says-
33.32. 6, you multiply by 2, right?
Negative 33.32. And that's because you multiply by 2 the coefficients here. And remember, just like the other two, you get the sum of the number of moles times the delta, either GH or S. Products minus reactants. Reactants are 0, so all you're doing is multiplying this by 2. In other words, delta G equals 2 times minus 1 times 0 plus 3 times 0. Okay. So that's your delta G. All right. With that information, you get delta G non-standard conditions. This one. So I'm going to freeze that. Who does not have an answer yet? Okay. Everybody's stuck.
Oh, because you have to divide that by this thing here.
For those of you who have an answer, did you pay attention to units?
Haha. You're funny.
That's why I was super confused.
Mhm.
Oh, like,
Is that
what is
a
happening?
I didn't and I need to, or is that a of course I remember?
That's of course I remember.
Excellent. All right, so if you plug in all the data, all the numbers, you get cover my notes right there. I'll move this up. You get that. I did the joules to kilojoules change right there. I left myself not enough space. Things disappear, things cancel. I should put the moles over here on the end. And when you do the calculation, there you go. Okay. What questions do you have about this problem? Okay. Then it'll make this disappear. Good. And same equation. Right, where do you go one? Okay.
I'm super confused.
Okay, so go back to this equation.
Today's Q.
Isn't Q equal K?
And since it's at equilibrium, that's what I'm saying here. You can rewrite this to say delta G equals delta G naught plus RT ln K. So Mike, this is, you were asking about this a little bit ago. Okay. If it's at equilibrium, what do you know about delta G? Zero. Okay, back up.
So I thought that you said. Never mind, I figured it out. So, well, I guess just to double check. So delta G with the circle is
Not.
STP.
Yeah.
Okay, and without it is
Else, that's
something
whatever,
else.
something else.
Okay.
How does it change? Like, what do we do? I honestly do not understand.
So you're looking for, like I said before, non-standard temperatures. So
Yes.
like 25, 35, negative 300, whatever.
Not zero
Not zero.
or 298 Kelvin.
273.
273 Kelvin.
Right.
0.15. Okay, got it.
So if it's outside of that,
Yes.
then you're going non-standard, and that's the difference between standard conditions,
Yes.
non-standard conditions. Okay, so this particular one is telling you that
We're
at
looking for-
25C, it's written to be at equilibrium. That's the standard, gives free energy at standard conditions.
At standard
Okay.
conditions.
It's at equilibrium, so this is the value of delta G, non-standard at equilibrium, 0. Okay.
Okay, so
And
at
at
equilibrium,
equilibrium, Q equals K. So
delta
you
G.
can rewrite this equation like the second one, and then since it's at equilibrium, you can write it like the bottom one. Then, this one can be rearranged to say delta G equals negative RT ln K. And then you can rewrite this, I'm gonna go to the side on this one. The ln K equals delta G over negative RT.
Wait.
Okay.
So
So all I'm doing is I'm getting you to the point where you can actually solve for K. So delta G standard conditions here, delta G non-standard is 0, it's equilibrium.
Yes.
Now you can take this one and rearrange it so you get delta G, little circle up there. Delta G is equal to this. I've just moved this to the other side.
Yes.
All of it.
Mhm.
And then I rearrange this yet again, divide both sides by negative RT, so I get ln K is delta G naught over RT, negative RT. And then if I want to solve it for K,
You raise 10 to that.
Or E.
No,
so
E.
I go E to this and E to that. When I do this side, it becomes K, so E to the delta G naught over negative RT.
So, K equals
Because when you do this one right here, in order to get the delta G by itself, I have to subtract RT from this side. If I subtract it from the right side, I'm going to subtract from the left. So I did the subtraction and just swap sides. But that's why this negative sign shows up. Okay. And then if you plug in the numbers, E to the, and I'm gonna take this all the way to 33,000, I got a 2 in there. I might can just write negative R times 298. .314 constant. So if you solve this, seven point something times 10 to the 5th.
what?
No.
No.
Yeah.
That's what I got. Did you guys multiply it by 1,000 to 33.32?
Yeah.
So 33,200 divided by. Yeah, because remember that R is in joules,
I get 33,320, not
33,320.
use a 200.
320.
Okay. Maybe that's it.
What I just typed in.
Because
I do
delta
get that.
G is negative, and then in this rearrangement that R is a negative RT.
Okay, I did get that. Where are your units?
So you know about equilibrium constants and units.
But what about on Kelvin and R?
That's what's supposed to be.
Are we just supposed to assume? Very nice.
There you go.
Oh, because he just rounded up to 1 decimal. He said, oh, so just said
So,
seven.
negative.
I missed everything on it. Just like
So there's 13 points, whatever, and then you take and raise E to that number. And it's about 7 to the 5th. Correct.
This might be kind of a dumb question. What kind of K is this? Like K is just like
Equilibrium constant is the equilibrium constant for this reaction at that particular temperature.
Okay, because it's different from like the other K's, right?
In this case, since it's not specified anything to do with the pressure, you think about it in terms of concentrations.
Okay, just the issue.
And you could, if you change the temperature, delta G is going to be the same, R is the same. Change the temperature, if you make the temperature bigger, then this number changes. If you make the temperature smaller, then this number changes.
Right. Okay.
Yeah. So it's consistent with what you've done before, and at different temperatures you have different values for K.
Right.
I mean,
Okay.
if you go back to whatever chapter it is in this text, well, there's at least one of the problems I put on the test that have different K values for different temperatures, and you had to figure out activation energy. Remember that one?
Or reaction rates.
That's what you're seeing here. This calculation. Okay. You good on this? Or try one more? Okay. I figured this way was easier than trying to do it on the slides, so this way is getting it doctored. All right, so delta G. And the question is, or the instruction, determine delta G and K. Right.
So delta G is negative on this, so it's 1.4. Right. Because we have double that.
It's free
And then
RT is given because it's 8.3 4 times 298.
Right.
Then we have a natural log of K, which is Q.
Well, this is the equation he gave us last.
What's Q?
That's what I'm trying to find out.
Oh.
Okay, well, that's what I got. I don't know what that's in.
So did you do a natural log of anything?
Because you end up rearranging.
Are you just being mean?
We don't know what Q is. We don't know how to find
He
Q.
gave us the
Alright,
delta G
we go
that
back,
we need.
back to the previous
We
one.
have the delta G right there.
Yeah, we have double G, but that's not the original equation that we need Q.
This is the equation he gave us last Thursday, or on Tuesday.
Okay.
And that was the equation he just used to calculate.
Probably have this around the other page.
So on the previous problem, just to walk you through the process again. In answer to the question, you know, all of the terms that go across, at equilibrium, someone mentioned this Q is equal to K. So you can just drop the K in right there. Okay. At equilibrium, delta G is equal to 0. Okay, so you're at equilibrium, Q is equal to K, delta G is 0. That lets you write this.
Okay.
Okay. So equilibrium, delta G naught plus RTLK. This gets rearranged into that form. And all I do is subtract RTL and K from both sides. Okay. And then since you're after, in this case, just the value of K, you need to isolate that term. And I do that by dividing both sides by negative RT, and I get this one. Okay. And then to get rid of the natural log part of it, I raise e to both sides, and I get this term right there. Okay. At this point, you have delta G up here at the top. You've got R, which is constant, 0.314, and you've got the temperature at 25 C or 298. Okay. Substitute everything in, and you get delta G naught and convert it to joules, and then you get negative R, put it right in, units are there, 298K. Solve that side. Even if you just solve this, you get 13.45 or something like that. 13.14, 13.45, whatever happens to me. And you end up looking up 7 times 10 to the 5th. The next problem is solved the same way.
No.
Okay. So it's at equilibrium.
But then if we're determining delta G, then it's just 0.
So you want to figure out. Put one little knot up there. Apologize, I get a little sloppy with the knot knots. I try to put them all in there, but it's another. Anyway, so to get delta G naught at 298, you need this information. And delta G naught for the equation, remember, is the sum delta G products minus the sum delta G reactants. The reactants are 0, and you've got twice that number. That's where I get the negative 106.44.
Yes.
Okay. Then, right here, this is my K equals E.
So we have to find K to find E. delta
No,
G?
you got, see now, at this point, Rosalie,
I'm so confused.
you have,
The questions
if you look at the numbers that
The questions
you
are
have at
so
your
weird.
disposal, I'm just gonna cover everything up with this. You have delta G naught.
It's not you.
Yeah,
You have R, it's a constant.
Uh-huh.
3.314 is a whole number.
yeah.
You got temperature,
Mm-hmm.
298 K.
Yes.
Okay. So at this point, the
Uh-huh.
only thing you don't know is the value of K. So K is equal to E to this.
Mm-hmm. But aren't we looking for delta G naught?
It's right there.
That's why I'm so confused.
There,
Determine
is
delta
it
G
298 Kelvin or determine delta G and determine K? I think is what the question is.
Right, and if you look at, like, here, did I give you the value of delta G for the equation? No. I gave you the values of delta G for the products in the reactants.
Yeah.
In order to get delta G for the equation, you have to do that.
Yeah.
And in order to solve for K, you have to know this number. So that's why my first instruction was determine delta G at 298.
And then you just wrote K. You just wrote K. Like, am I supposed
Like
to
it's Kelvin.
determine K?
Is it 298 Kelvin?
And-
it as?
I was so confused. This is why I've been like asking stupid questions because I didn't realize what you were trying to do.
To be fair, I thought he was putting 298, and he just decided to pay underneath. So that's why I got confused. I was like, oh,
Okay,
he's not
okay.
in the room. He's just being lazy.
All right, so is this a little more clear then? Determine G and then determine K?
Yes. But I thought the point of determining K was we find G anyways.
You can't figure out K
Yeah, there you go.
because of this.
No, we find delta G naught to find K anyway, so you don't have to tell us to do it, right?
I converted those.
I feel like this isn't right.
Correct.
Okay.
But
Okay, equals.
Rosalie, you have to realize that there are some people who look at this and go, what? So the first step is figure out delta G.
Okay.
And then secondly, figure out K. There it is. All right. What questions do you have? Jesse? K values that typically are given it to? I mean, I don't. Typically.
Can I ask another simple question?
Sure.
pH always goes to another one.
That's kind of the convention with pH. Go to the hundreds. Can you go out further? Yeah. Can you go to the tenths? Yeah, but the convention is go to the hundreds. I mean, even if you look at all of the, if you look at the pH probes, which you use, they all report to the hundreds, even though mathematically you can calculate it figure out. It's just kind of convention to say hundreds. Okay. And generally, when it comes to significant figures, I'm a little flexible if you're like 1. But there are some people who are reporting like whatever this answer is. Okay. Like the previous one, they write down all of that stuff. Like 6.92906. No. I could live with 6.9 times 10 to the 5 or 6.93 times 10 to the 5. Two digits is kind of the convention for K values. Hundreds for pH. Okay. Any other questions, Mike?
Why is the equation given two different forms if at equilibrium K equals Q?
I don't have a good answer for that one.
That's ridiculous.
I
I want to know the person who did that because I have something.
I'm not doing that.
Say that again.
I said I want to know who wrote that because that is confusing and I have something for them. I mean, legitimately, all they did is make one term negative and add Q or K or whatever.
Yeah.
But
Uh,
it's
And it's
You know,
negative.
and it's like on the previous one, and that's why I say I don't have a good answer for that because even
Divided
here,
by
was that one or the previous one?
8.3.
This one. Because even here with those pressures, you still are assuming that it's at equilibrium, but it's not standard pressure at equilibrium.
Just brings it
And all I can think is that the Q is going to be let's see, even 10. And this is like why even the 25C for electric chem versus 0C for everything else. I don't have the answer for that. I've searched for it, to be honest. I'm like,
I
you
know.
go to
Boy,
Google,
what is
look what
that?
standard conditions are. Yeah, we'll see.
So, at equilibrium, Q is 0, right? Is that's not right?
Q equals A at equilibrium, and it's standard. See, this is where it's weird because also standard conditions. For these, you got 1 mole and 1 mole. Anyway.
So I mean, that should mean that.
That's just.
Right. Right. So,
So it's just an expedient way to find either K or Q, so.
right.
So like I have an answer, and I just want to know. Okay, so I know you said it's just like a normal K value, but like, so how would you, with the equation we're given, how could you say that like it favors products over reactants type of thing? Is that just because of our knowledge? We could say that just because of our knowledge of the K value, or?
Yeah, and when you look at that number,
You say it favors
product
products,
favor.
right?
Gotcha.
And that's just at that temperature and pressure, it highly favors.
Right. And you can compare different temperatures to see, you get a different K value at different temperatures. You
Right.
can make predictions about which set of conditions, high temperature, high pressure, low temperature, low pressure, high temperature, low pressure. I mean, whichever conditions are going to be more favorable.
Is that kind of why weird stuff starts happening at 0? I mean, not, obviously we made this equation to model it, but
Yeah, it's there.
makes the equation blow up.
Since motion stops and you get into differences in things like intermolecular forces, so liquid like gases behave in weird ways, they climb walls, they do some weird stuff.
That's pretty cool.
All right. Yes. In a moment. That's kind of the end of the thermochemistry 2 chapter. Manipulations of that particular equation. Okay. Pardon? So 16 in this text is thermochem. This was right at the end of that. The first part of thermochem, remember, was back in 162. Okay, so this is the last little bit. The other thing that I was hoping to at least real quickly before I say take a break. Just because I want to know okay. Could you balance that in acidic solution? Remember how to do that from way back? Okay.
I literally have no idea.
Yes, that really long product, 161.
Yeah, H2O.
And you gotta add some H2Os, you gotta add some H's, you gotta
So
add.
you separate it first. Wait.
So first
You
you have to
first separate it. So you go CR2O7 becomes CR3.
Okay, so hold on. If you don't remember, what happens to the iodine? Is it oxidized or reduced?
It's reduced. No,
Oxidation is reduction is gain.
Look at the oxidation numbers.
It's not the
This is
electrons.
a 1 minus and it goes to a 0. Oxidation is when your oxidation number becomes more positive.
Okay, so oxidation.
Reduction is when your oxidation number goes more negative. In this case, it's a 6 plus, over here it's a 3 plus. So what happens to the iodine? Reduction or oxidation?
oxidation.
This is oxidation. What happens to the bottom one?
Reduce.
Reduction. Okay. And when you balance in half reaction or by half reaction method, you split them apart. And the process, you balance everything that's not, I'm going to cover up the bottom one first. Everything that's not hydrogen or oxygen. That's the first thing. Which means balance the chromiums. Put a 2 there.
Oh no, I remember this. Oh no.
Chromiums are good. Next step, remember that.
Add water.
Add water.
Add water. How many waters do you add? 7. And I add 7 waters because there's 7 here.
Then you add
So
14.
waters are good. Then what do you add?
14.
Hydrogen.
How many hydrogens?
14.
14. So you say 14 H pluses. Now you look at charges. I've got a total of 6 plus on the right. I've got a total of 12 plus on the left because I had 14 plus the 2 minus.
So add 6.
6 electrons to the left.
Plus I put 6 electrons, right? So that one's all done with respect to electrons and everything else. Bottom one,
Put a 2.
put a 2 here, right? And then what?
Add 2 electrons to the right.
To which side?
To the right.
Right, so I go plus 2 electrons. Then what do you do?
Combine it.
Line one, two.
Not yet.
You have to multiply it so the electrons are equal.
Yeah.
Remember, you gotta have charge balance. You gotta multiply to make the electron counts equal. In this case, you gotta multiply the bottom one here by
3.
3. So this becomes 6. There's 3, and that's 6. Then, whoever said combine like terms and get rid of things, that's what you do next. So you get rid of, cross these out in red, 6 electrons go away. And when I rewrite this with everything as it should be, okay. How's that, Jared?
So what, are you able to write the steps one more time? Is that be too long for you to do, like?
Okay, so 1, you need to split into reduction and oxidation reaction. So you got to find the half reactions. That's the purpose for going up here and looking at oxidation numbers and saying 6 to 3 is a reduction and negative 1 to 0 is an oxidation. Okay, so that's the first thing. Second thing, you balance the not hydrogen and oxygen. Okay, and then number 3, you balance oxygen with water. Number 4, balance the hydrogens with H plus. Okay. Next step, balance electrons, or I should say charge with electrons. So like on the top one, you put the 2 there to balance the chromium, you put the 7 waters in to balance the oxygens, you put the 14 H's over here to balance the hydrogens, and then 6 electrons to balance the charge. Do the same thing for the other one. Number 6 would be to eliminate and combine.
So, is this gonna be on the test tonight? Like,
No, not tonight.
Oh, okay.
But this is,
Did you get the?
you need to be able to do this kind of thing for electrochemistry. You need to be able to recognize reduction and oxidation. And I was hoping to get electrochem tonight, but I'm not gonna make it. So, anyway, this is the start of it. I need you to think about this for Tuesday. Okay? All right.
Where'd you get the 6 plus under the CR207?
6 iodines?
No, go up. The oxidation number.
Oh, okay. You don't remember this? Okay. When you're looking at oxidation numbers, a little bit of math. The sum of the oxidation numbers has to equal to one of 2 things, either the charge or 0. In this case, you've got a 2 minus charge. In 99%, I guess, of all of the things you'll deal with, oxygen's a 2 minus. So that gives you a 14 minus total charge.
That makes sense.
Okay.
Okay.
Then you gotta add a 12 plus to the 14 minus to get a 2 minus. 2 chromium, gives you each one of the 6 please. Okay. So, those are your steps. I think in my slides I might have it as 7 or 8 steps, but that's the essence of it. You look at the oxidation number, split it, balance, balance, balance.
Okay.
Put it all back together. Okay. It's not on tonight. Tonight's just buffers. That's all it is. Buffers. That's it. Victoria.
Did you do it where like if you did
There's buffer multiple choice. I'll make that optional if you want. Actually, have we done buffers twice or once?
Once.
Do this one. I'll go optional if you've done it twice. So like the acid base, there've been 2 acid base ones. I want 2. So, but there are only 4.
So we have to do.
Yeah. Yeah. So do all 4 multiple choice and do the problem. There's one problem, multiple parts. Kind of like it's like last week. Very similar. So remember last week I said the acid base multiple choice was optional, but that's because I had 2 data sets on it already. If I had 2 data sets on buffers, that's the same. But, all right, take a break. Come back and do.
That one on the back of the test.
Standard temperature point or something. Standard. Oh yeah. Zero. I don't know.
I'm only doing one test today. I wanted to do both.
Probably better to only do the one since it's
Oh.
literally the same test. That way, if you mess anything up, then you can fix it.
I mean, if I do well on this one, I don't think I'd even need to do the other ones. Doesn't he change the scores back? Technically, that would be the first one.
Also, okay.
But logic, it dictates I don't need to.
Your logic would say, look, you have to make this score multiple choice on the last one. I'm good, I don't need to retake it. Or even since this is the same test, be like, let's just not roll the dice the second time. I'm happy with score 1. Let's not worry about score 2.
Because like technically the one I'm taking today is the second one. And when you take the second one, it this person moves it raise the other one. So if I do really well in today's, theoretically, I don't
Data sets.
theoretically I
You
don't
actually
need
do it.
to do it.
Although doing it twice will help you for the final.
True.
Because I'm looking at this and I'm having to like re-walk through everything that I did.
The thing that confuses me the most is this. Like figuring out what's reacting to what. That confuses me. Everything else I'm pretty okay with. I understand all this stuff. It makes sense. I understand sort of that. I don't know how it got to point 0.01.
How do you have the OH and F?
Yeah.
Where did you get this from?
This is SI system.
Oh, okay.
And it always confuses me how to find these. I don't have the actual, equation written down, so it's hard to.
So that's the acid and base equal fluorine plus water. Fluoride plus water.
But
And water is just not in there.
yeah.
So that's just doing the reaction in reverse.
It's so like he somehow picked these out of like an bigger things, and I'm like, how did you choose those ones? Why those ones? That's what confuses me.
Oh, I bet I know what type of question. Luckily, that shouldn't be what our buffer question looks like.
Oh my god, because that was confusing. I was like, I don't know how.